All right. Now, my objective here is actually to show you an easy way out to deal with Laplace Z transforms, right? That is the whole purpose. So that I expect you would be able to deal with Z transforms without any major issue, right? Right. So if you see what's on the screen, 1, 2, 3, right? These are some of the steps that we follow uh, in getting to the Z transform of a function, right? Any discrete uh, 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 series of samples, right, can be transformed into Z domain and get the Z transform of that, right? Now, this is how we do that. First step is the sampling. You have FT, continuous time function, and you get the samples out of that. If you look at this equation, sometimes it is kind of intimidating, right? But if you see what this actually is, it is the set of samples, isn't it? Now, if you look at FKT is the size of the sample at time k, okay? So at time k, signal has a value, all right? Time k signal has a value. So if I draw it here, say if this is the signal and this is time kt, right? This is k and t, right? So this is the value of the function at that moment of time, right? This is the value of the function. And this is actually fkt, this one. Now, as I said earlier, you also need to tell the position of that sample. So position is kt. So this is the position, kt. And you write it like that, delta t minus kt. So there this t minus kt, when you say t equal t minus kt, right? The whole thing, sorry, is equal to 0, right? T is kt. All right. So this is the position. Now this is just one sample, the magnitude and the position. Magnitude, this one, right? And the position, this time, kt. This whole thing is just one sample. And there are a lot of samples like that. The sample just before this one and after this one, right? They all have the same format and only variable is k. Only variable is k. You start k from 0, somewhere here, and go to very high value. Right? For each k, you have the position of the sample and the magnitude of the sample. Right? So you have k from 0 to infinity. All right. So this is what happens. This is what happens. The entire set of samples is here, right? That is number one, sampling. And number two is taking the samples, right, and prepare them in a continuous format. So, which means from one sample to the other one, there is a zero line connecting them together. There is a zero line connecting them together. For example, I can draw it like this. You have one sample here and another sample here. You connect them like that. This is zero, right? Zero level. One sample, the other one, right? But actual discrete signal has no such thing. So two samples, in between there's nothing, right? In between there's nothing here. This is the discrete sequence. This is the discrete sequence, but adjacent samples are connected using the zero line. And because of that, you can actually use Laplace even in here. Okay. So when you do that, you get e to the minus skt. You get that? So this is the delay. So all the samples k plus 1, k plus 2, and so on, right? Samples, and this is their position kt, right? 1t, 2t, 3t, 4t, 5t, like that with minus s. When you evaluate this one, you get the Laplace transform. But as I said to you, we are not walking down that path. This is just to show you what you get if you apply Laplace. Instead, what we do is number 3. There we use fkt, the sample values, right? Sample values, first sample, second, third, fourth, and so on. And together with it, with each sample, you write z to the minus k. So this is actually the position. K equals 0, 1, 2, 3, 4, 5, 6, like that. The magnitude and the position. All right. And you get the summation from k 0 to infinity. So this is pretty easy. This is pretty easy. If you know the set of samples, let's say you have a sequence of numbers. Okay, sample from a waveform, right? So sample from a waveform. You have these values, samples, and you know the positions. Then you can write down this expression is set of samples added together. Okay, so it's pretty obvious now that anybody should be able to evaluate the Z transform of a set of samples. If I give the sample sequence, you should be able to calculate the Z transform of that sample sequence. Okay? Any questions? Fine. So it's just one single equation you need to remember. It is just this, right? Capital X of Z. This is the Z transform of your signal. This is analogous to Laplace transform, right? Capital letter to represent the signal within bracket S. And now we have the same representation, capital letter within bracket Z. And on the right hand side, it is summation. This is easier than Laplace because Laplace is integration. Laplace is integration, okay? Whereas this is just summation, which is easier to calculate. And summation of what? Xn is to the minus n. See how easy it is, right? Xn is to the minus n. N is anyway the independent variable. It goes from 0 to 1 to 2, 3, 4, infinity. And xn means the value of the sample, nth sample. Okay, when you get the samples, you know the values, right? This is those values. And z to the minus n means the position. So this mathematical operation will give you something, and we call that xz, the Z transform of the sample sequence. Okay, right. And the last thing I want to tell you right here is that this is a power series, you know, xn is to the minus n. It's a power series. Is to the minus 1, minus 2, minus 3, minus 4. It's a power series. So therefore, the expression may or may not converge to a finite value, right? If it converges to finite value, then the Z transform is defined. For whatever reason, if it does not converge to a finite value, right, then the Z transform does not exist. Okay. Now, rather than saying whether it exists or it does not exist, very often the case is the Z transform exists for some values of Z, when you take power series of something, right, the total expression, whether it converges to a finite value or not, depends very much on the value you selected, value of Z, okay, value of Z. So for certain values of Z, the Z transform can exist. For certain other values of Z, the Z transform would not exist. Okay. So therefore, there is what is called the region of convergence. We call it that way. When you evaluate Z transforms of signals, you also have to tell what is the region of convergence. Okay, that is, what are the values of Z for which the Z transform is finite. Okay. Right. So I think I explained this to you. The other thing is poles and zeros of Z transfer functions, right? XZ. This is very similar to the S domain transfer functions you have been through. You have the rational polynomial of S, numerator and denominator, and you figure out you factorize the numerator and calculate the zeros, and you factorize the denominator, and you identify the eigenvalues, poles of the plant. Okay. So here the process is very similar, right? You have the rational polynomial of Z now, not S, Z. So when you have the polynomial of Z or S for that matter, you can have it like positive powers of S or Z or negative powers of S or Z. Okay. So same function can be written here. You can see it's a positive powers, but you also can write it in negative powers. If you multiply both numerator and denominator with say Z to the -2, you convert this whole expression to negative powers. Okay, right. So this particular example is very easy example, right? 3Z square minus 13Z minus 10 over Z square plus 2Z minus 8. You have to calculate the poles and zeros, right? So what you do is you break the numerator quadratic expression into two first order terms, 3Z plus 2Z minus 5, and the denominator quadratic into two terms, Z plus 4Z minus 2. So if you get the denominator Z plus 4, Z minus 2, and set it to 0, you can calculate Z values of Z, right? For the first term, sure, to make to 0, Z equals -4. The other one is Z equals +2. So these are the two eigenvalues of the Z transform, and we call them poles. Okay. Now, if you look at this -4, you know it's negative half plane pole, and this is a positive half plane pole. If it was a S transformation, right? Like transfer function in S domain, we clearly decide the plant is unstable, but not so in this case where the transfer function is discrete. Okay. So if you have the Laplace transformation and do the discretization, and you have the discrete version of it, after going through some sampling time t, right, you have a different transfer function in Z domain. So for that matter, right, you cannot take all the rules that you use in Laplace domain here and judge stability and so on, right? You have to figure out what are the new rules here, right? So therefore, we don't say anything about stability or anything right here. We just calculate the poles and zeros. And for zeros, you take the numerator 3z plus 2 and z minus 5 and set them to 0. You get the values for z, right, as minus 2/3 and plus 5. Okay. So I'm going to give you this example. Please take it down, right? Get a piece of paper, work it out. So there are a few functions here. How many? 1, 2, 3, 4, 5, 6, 7. 7 functions, right? They're all discrete signals. And each signal is actually given to you. These are the samples, 1, 2, 5, 7, 0, 1, right? These are the samples of the signal. And you see this arrow, upward arrow, and that is time 0, t equals 0. This is the t equals 0 position, right? This is t equals 1, 2, 3, 4, 5. So you can say this as k equals 0 if you want, right? K equals 0. Now here you have the delta function, delta n. This is delta n minus k, delta n plus k, right? And here you can see this is delta at time 0, so which means if you have the timeline like that, right, this is time 0, right? This is 1, so this is delta. This is delta n. Whereas this one, delta n minus k. So the delta happens not time 0, but when n equals k, right? That delta is located at n equals k, maybe somewhere over here. This is k. So this is n. N is the axis variable. When n equals k, you have the delta. So this is that. This is delta n minus k. Okay, remember that. So I think these are the little confusing things to you. Now you can get a head start. So you are asked to calculate the zTransforms, right, of the function. So take the first one. Please write it down. X1 is this set of samples. First sample 1, then 2, 5, 7, 0, 1, right? N is the time index. It goes from 0 to 5. This is 0, this is 5, right? Which means x0, so this x1, 0, this 1 means the first signal. This is the second signal, third signal. That's why these 1, 2, 3, 4, 5, 6, 7 are there. So don't worry too much about it. The first sample is 1, second sample is 2, third sample is 5, and so on. Okay. So first thing you need to do is to identify the samples, discrete samples. Okay. And second step, you use the definition of the zTransform, which is summation from n0 to infinity. In this particular case, we have only 5 samples, right? But the definition says 0 to infinity. So we work it out 0 to 5, x 1n z to the minus n. This is the definition. So you cannot forget it, right? Because it's so simple. So now expand it and substitute, right? The x1 0 is z to the minus 0. That is the first uh, term. Second term, x2 is z to the minus 2. Third term, x3 is z to the minus 3. So it goes like that, all 5 terms. Please write it down yourself. Get a bit of practice. If you haven't done this thing before in math modules, right? This is the time to catch it up. Once you write it down, this summation, then you substitute for first sample, second, third, fourth, like that. You get to this expression. Now you see it's a polynomial of z to minus powers. Z to the minus 1, Z to the minus 2, minus 3, minus 4, minus 5. Right? So this is the Z transform of the first signal. Now see, now you are able to do this for any signal sequence given to you. Now you can calculate the Z transform, right? And the second thing is to figure out the region of convergence, ROC. Now just look at it. Is it minus powers? Minus powers. So what if Z equals 0? If you put a value for Z, right? Say 0. 0 to the minus 2, minus 3, minus 4, minus 1 means 0 is in the denominator. You can't have a 0 in the denominator, then it's not defined. So any other Z, right, will give you a finite solution here. Finite value. Complex number, basically. Z is a complex number, right? Complex or real, it doesn't matter. It gives you a finite value for any Z except 0. So you write it like that. The region of convergence of this Z transform is entire Z plane. Z plane is a complex plane, right? Similar to S plane. Like this. This is the Z plane, right? This is the real part, real axis, or this is the imaginary axis. This particular Z transfer function is not defined here at the origin. It said equals 0. It is defined everywhere else. Any questions? Now, are you able to calculate the other Z transforms? Take the second one, please. Start working on the second one, x2n. This is the sequence, and I want you to calculate the Z transform and find out the region of convergence. I'll give you a couple of minutes. Let's take 2 minutes for that. All right. So the process is very similar, except for this difference. Uh, Sample at the middle is actually time zero. So these are negative samples, negative time, the positive time. Okay, that's the only difference. So now you see x 2 of -2. This is -2 point, right? 2 steps to the negative side. This is 0. Is 1, then you have 2, then you have 5. This is the time 0 sample. Right. So then when you put it into the equation here, the summation is set to the -2. So remember that the time shift is -2, but there's another minus anyway in the summation, right? Is set to the -n. It's in the summation. So therefore, negative time, they have positive exponent eventually because two negative signs on the other side pretty much the same, and eventually you get something like this. So z square plus 2z plus 5 plus 7z minus 1 z minus 3. And when you see this one, the region of convergence, again you can see, check the values for z. That will bring the expression to infinity, right? So definitely z, if z is infinity, right, the expression is infinite. So therefore we can't take that. And not only that, when z is 0 also, right, these two terms are not defined. So therefore, this particular time series sample sequence is not defined for z equals 0 and z equals it goes to infinity. So that's all I have to I want to tell you about this. I recommend you work out all of these things. Anyway, we'll work out some of these things down the line here, E, F, or G, right? Right. Let's take E. There are the time sequence is sample sequence is delta n, just one sample, delta n. That is this one. We want to calculate the zTransform of the delta function. Right. So the definition you already know. I have drawn it and explained it to you. Mathematically speaking, delta function is 1 for n equals 0 and 0 elsewhere. Okay, negative, positive, it's 0 everywhere except for time 0, and that position, the value is 1. Okay, but we have no double or triple or multiple standards. We use the same equation and substitute for it. Let's say if you use double-sided C transform, which goes in minus infinity to plus infinity, right? The entire time axis. Yet you have only one sample, non-zero, which is at time 0, right? So eventually it will be delta 0, right? N equals 0, delta 0 is set to the -0. Okay, so delta 0 is the only sample which is 1 and is set to the -0. Any number to -0, right, is 1. So therefore the answer is 1. Okay, so you can see this in zTransform tables that the zTransform of a delta function is 1. Delta function is 1. Now, if the delta function, right, is shifted, the zTransform is not 1 because the zTransform is connected with the position of the sample, right? So when the position changes, the zTransform is also changing, right? Therefore, please work it out. All these exercises. Now we have done 3. You do the other 4 at home, right? Homework, exercise. You don't have to submit anything. Any questions, please?
So they are in the example B. Usually, from the definition, it's from summation from n equals 0 to infinity, right?
Yeah.
There's a we took from n equals -2 to then 3. It's how it is.
Oh, well, the definition, you have double-sided C transform or single-sided C transform. Okay. When you go to double-sided, sometimes it is not kosher, right? So most of the practical applications, you have 0 to infinity, right? However, if you know for sure you have only few samples, right? For formality, you write the summation 0 to infinity, but when you work it out for whatever samples available, right? There's a defined range in time, right? Maybe 0 to 10, 2 to 5, or whatever. It doesn't matter. Whenever there are samples at different positions, you take those samples, right? If it is a sparsely distributed set of samples, one is at -100, the other one is -5, then there's another one at 10, there's another one at 250, sparsely distributed samples. Yet you take these samples and put Z to the minus the position, the time position. So stick to this equation, right? And apply to Xn the existing samples. Every existing sample should be considered here. Is that what you asked?
Yes, sir. Got it. Yeah.
All right. Any other questions, please? So make sure now you don't have to remember a lot of things, right? But you learn the skill, right? I'm referring to the skills, right? Now I want to assume, I want to believe that you are able to do this, given the sample sequence, the least, right? You can derive the Z transform and figure out the region of convergence. So maybe you can add that to your to-do. I know how to list, right? I always say this to students, maintain, I know how to list. I know how to. I know how to 1, 2, 3, 4, 5, like that. You write it down. Now you can add one item. I know how to determine the Z transform of a sample sequence and then figure out the region of convergence. Okay, so I'm sorry about my handwriting because these equations are very long. I don't have time to write down using the equation editor. So I get the photos from the uh, from my textbooks. I think they are still readable to you. Okay, so what do we have here? You have now. I want to take basic or very popular functions, right? Like delta function, we already dealt with. Now it's what? The step function, UST, right? The name given to a step function is UT, and some books you will see UST, a unit step function. And if you send this through a sampler, every time t, it closes and you read the sample and then opens. There's no sample, nothing for capital T time. Okay, so this is what you get as the output of the sampler. Okay, and in between, maybe you can connect them like that so that you put a star here which says still continuous. It's continuous signal, right? Because zero line connects the samples like that. Okay. Because otherwise you can't use the Laplace. That's why, okay? So what is US star T? This signal, mathematically, right? It is the summation of all the delta samples. They're all delta, right? Because the height is 1, magnitude is 1, but they are positioned at different times, t, 2t, 3t, and so on. So the position information is given here, delta t minus kt. K is the position, 1, 2, 3, 4, like that. Okay. The magnitude is just 1. And we know that the Laplace transform of delta t is 1. We have done it already in the previous semester. And now, what about delta t minus kt, right? That is when you shift it by a certain amount of time, right? Same delta, then you know the delay comes in front of that, e to the minus kt. This is again from Laplace. And then the Laplace transform of unshifted sequence, that is delta t. Okay. So this, when you say delta t, it is at time 0. And the Laplace transform is 1. Now, when you say delta t minus kt, right, it is shifted delta to kt, time kt. And if you recall your Laplace, the time shift, remember that? The Laplace transform of a time shifted sequence is equal to the Laplace transform of time unshifted frequency pre-multiplied by e to the minus st. Remember that? So this is just that. S is equal to kt. Therefore, you don't have S here. Instead, you have kt. And the Laplace transform of the unshifted sequence is 1. So therefore, it is simply e to the minus kt. E to the minus kt. This is for one single shifted sample. One single shifted sample like this. And the Laplace of that is e to the minus kt. Okay, can you see that? So if you take this one, it is e to the minus t. If you take this one, it is e to the minus 2t. If you take this one, the Laplace is e to the minus 3t, and so on and so forth. So again, if you look at the superposition theorem of Laplace, it says if a function has multiple components and they all have separate Laplace transforms, you can add them together to get the Laplace transform of the compound signal. Okay. So you add them together, e to the minus kts, all of them, right, from 0 to infinity. And then what you get is the Laplace transform of the sampled sequence of unit step. Okay. So this is what we are trying to use the Laplace transform and the properties to figure out the Laplace transform of sampled unit step. Okay. Now, in mathematics, and we deal with sequences, right? So I think you're ready to deal with that kind of thing. This is a sequence, right? You have the ratio between these two, right? E to the minus t, and then e to the minus ts. It goes like that, right? Sequence. So how to add the sequence? I think this is a O level question, right? Remember, simple sequence and compound sequences like that, how to get the summation of the sequence if the common ratio is less than 1 and so on, right? So when you have this sequence, you want to calculate the summation, right? You multiply this one with e to the minus ts and then deduct the second one from the first one, and most of the terms cancel out like that. And you can see it over here, e to the minus ts times u star ss. This expression, right, minus this expression. So then you get 1 minus e to the minus ts times the summation. Which is equal to 1, right? Because you get these terms cancel out. And if you look at these cancellation, uh, it, it, it works out one step offset between the two sequences, this one and this one. Like second term on the first sequence cancelled out with the first term of the second sequence. It goes like that. So eventually it leaves the first sample or the first term of the first sequence and the last term of the last sequence, somewhere over here. These two terms do not cancel out. Right? So therefore, the result on the right-hand side is 1 minus the last term over here, second sequence. And if you look at the last term, it is e to the minus infinity times ts. E to the minus infinity times ts is the last term. And if you don't want to write it over here, right, by the side of 1, there should be a reason. And that reason is that this term is 0. You have to make it 0 if you want to move forward from this point. Otherwise, you have to just stop and leave it. So we assume that e to the minus ts, this one, this is a complex number, but the magnitude of this is less than 1. E to the minus ts is less than or equal to 1. Okay, in fact, this has to be less than 1. Okay, when it's less than 1, when you multiply it, right, infinite number of times, it becomes 0. It becomes 0. That is why you don't write it over here. So 1 minus 0. Then the Laplace transform is us star s, this one, is equal to 1 over, this term comes to the right hand side, 1 minus e to the minus ts. Okay. Now, we don't take it forward, as I say, because we don't want to bring an s term in the exponent, e to the minus ts. This is invitation for problems. So therefore, we substitute z in place of s here. So e to the minus e to the ts is z. That is the definition of z. And because of this negative sign, the negative sign stays there. So it will be z to the minus 1. All right. And you can write it this way or this way. Okay. So negative power of z or positive power of z by multiplying numerator and denominator both by z, you can convert this to that. All right. So this is the z transform of a sampled unit step. Somewhat easy to remember. Z over z minus 1. Z over z minus 1. Any questions, please?
Excuse me, sir.
Yes.
In a Laplace transform of delta t minus kt, is it e to the minus kt s? Otherwise, I mean, we did
This one, right?
Yes.
Yeah. So this is the delta t minus kt. So it is a delta function appearing at kt, time kt, right?
Yes.
Right. So in Laplace, there's a theorem called the time shift. You know that, right? So the
Yeah.
time shift theory says in Laplace that if a function is time shifted, its Laplace transform is constructed using the Laplace transform of the unshifted function. Unshifted. So before shifting, it was like this, delta t. Okay. Use the Laplace transform of the unshifted one, which is 1, and multiply it with s to the minus t or tau, the delay. If it is a delay, it is minus. If it is advancement, it is not minus. So we use that technique here. Because we know the delay. Delay is kt. So yeah, this is s to the kt, right? No. This is right. This is right. It is e to the delay, time delay. So
Yes.
time delay is kt.
Okay. So if so, in the other line, delta t, Laplace of delta t plus
Yeah,
Laplace of delta t minus t, it's s. Uh, how that is?
yeah. Because this is without k, because you know k. K is say over here k is 0. This is k1. This is k2, k3. So this is k axis.
Yes, minus t. Okay. So, the s comes from.
Yeah. So now up to this point is okay, right? E to the minus kt is all right.
Sir.
Now what we do here is that, right? We write this for every k, right? So in Laplace, you can see it over here, right? Um, so these are the delays, right? Without k, this is single delay t, 2t, and so on, right?
Yes.
So we substitute for k, right? So the delay is over here. So this is the first time, first step, first sample rather, t. So it is t times s. And this is the second sample. You can see the delay 2t times s, right? So in Laplace, you see the shift theorem, it is e to the delay times s. Delay times s. Oh, there should be s here. Hold
So
on a
that's yeah,
second.
yes.
Okay, right. So give me a second. Right. So there should be s over here. All right. There should be a s over here.
Okay, sir.
So remember that you just write e to the delay times s, right, in front of the Laplace transform of the unshifted sequence or sample or whatever. In this particular case, these are all single samples, so the Laplace is 1. So please remember these, some of the simple things you can remember, uh, like this, for example, right? That the Laplace zTransform of a sampled unit step is 1 over 1 minus z to the minus 1, or z over z minus 1. Either way, it will help. So if you look at this whole process again, you will see that initially we start with the Laplace, because we are much familiar with Laplace, and then through the process at some point we just substituted Z for S, Z for S, and we quickly got the Z transform worked out, right? So there's a very strong relationship between Laplace and Z. It's just a little tweak in the equation. Now, the other thing I want to discuss with you, because I don't want to take you too long with the Z transforms, right? Because of the obvious reasons I already explained, but I just cannot drop this one. So therefore, let's look at that also. This is exponential functions, right? Exponential functions. So I have here a numerically defined exponential function, right? Half to the n, right? So I could have taken a symbol over here, but I'm taking this from some other reference. So I just left it unchanged. So half to the n. So if you write down all the samples, the first sample is when n equals 0, right? U0 is 1, half 0 is 1, so it is just 1. Second sample is n equals 1, right? Then it is half. Third sample is half to the square, half to the 3, and so on. It continues like that, right? This is the sample sequence. Without this half to the n, right, it would be just un, then it is 1, 1, 1, 1, 1, all ones. But now it is a decay, right? It decays. Every step it decays by half of the previous height. Then now we put what? The technique that if you know the delay in Laplace, it's like this. This is the delay, okay? E to the minus ts, e to the minus 2ts, okay? This is how the delay is represented. Now, if you look at it over here, e to the minus ts, right, is also written as z to the minus 1. Z to the minus 1, because this is actually the delay. E to the minus ts is the delay. Okay. In Z domain, it is Z to the minus 1. Now it is pretty obvious. Z to the minus 1 is the delay, isn't it? You see this one, e to the minus ts. This is the delay with respect to this one. Okay. With respect to the first sample, it is one time delay, e to the minus ts. And this is actually z to the minus 1. This is z to the minus 2 with 2 steps from here, 2 steps. This is z to the minus 2. So by definition, z to the minus 1 is 1 step delay. Z to the minus 2 is 2 step delay. Now, if you remember that, your life will be very easy with Z transformations. Z to the minus 1 is delay. I'm sure you may have seen this in books and other documents, right? Z to the minus 1. When you get the signal from the output and feed it back to the input, you sometimes have seen in books Z to the minus 1 block. The signal goes through that block just to say it is a delay, right? You cannot feed back present signal, but what you feed back is the previous signal, right? So you have time delay. So therefore, this signal here, right, half is delayed from this one by one step. So you can say that this value is half. This is only the value. There's no time information here. But if you put time information also, you can say it's set to the minus 1 with that signal. What about the third one? Half to the square. This is the value or magnitude of the signal, but it is 2 steps delayed. So you write down is set to the minus 2. So this makes life a lot easier. All of the samples at their respective values, positions, are multiplied with z to the minus 1 or 2 or 3 or 4, depending on the number of steps they are delayed. Okay. Now, in quick succession, you have converted the sample sequence into the Z transformation. It's much easier. You just need the sample sequence and then put Z to the minus 1, 2, 3, 4, 5, 6, like that. You have the entire sample sequence. This is infinite sequence. So you finally say plus dot, 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 right? Now you want to find out the summation of this one. How to do that? How to get the summation? You can see half is set to the minus 1 is the ratio. This is the ratio. You multiply with this, right? Every step, right? When you advance, you multiply the term with half z minus 1, right? That's how you get the third term from the second term, and so on. Right? So you can see the entire sequence can be written like this, and from 0 to infinity, half to the n z to the minus n. Pretty simple. Right? This is the rate, the magnitude drops, and this is the position of that sample. So n is common, so that you can take it out of the bracket, leaving in the bracket half z to the minus 1. Half z to the minus 1. Now this very much looks like 1 plus a square plus a3 and so on. And the answer is 1 over 1 minus a, provided the magnitude of a is less than 1, for the very same reasons we discussed earlier, right? The common ratio has to be less than 1 for the sequence to be finite. So now this a is half z to the minus 1, right? So put it there, half z to the minus 1, right? So this is the z transform of the exponential sequence, sampled exponential sequence. Clear? And then if you look at the region of convergence, you can see that half to the half z to the minus 1, this common ratio has to be less than 1. So then you can adjust it to say that magnitude of z, right, has to be greater than half. So if it is less than half, the sequence is not going to converge. All right, it is going to diverge, and therefore it is not defined. Because the sequence is infinitely long, that's why. Okay. Right. So we have figured out the Z transform of an exponential function, Z transform of delta, Z transform of sample unit sequence, right? The major functions. So there's another homework for you, right? You can see it graphically here. 1, 2, 3, 4, 4 functions, right? So find the Z transform and the region of convergence for each other discrete time sequences, right? Please do this as a homework, and there's no requirement to submit it. This is for your practice, okay? Spend some time, because I'm sure you don't frequently touch upon this content, and you might have already forgotten. Your familiarity is not that good. So spend some time, right, before next Sunday, uh, to get yourself familiar with the C transforms and mathematical manipulations. So this is just a repetition of what we just did, exponential sequence, right? Just to consolidate your knowledge about it. So we have yk 0 for k less than 0, nothing on the negative time, right? And on 0 and positive side, it is e to the minus kt for k greater than or equal to 0, right? So this is our function. And if you want, you can calculate the samples, right? Put k equals 0, 1, 2, 3, and so on. And this is yk, e to the 0, e to the minus 0.25, e to the minus 0.5, and so on, right? These are the function values. And when you draw it, you will see it like this. It is decaying function, okay? Decaying function. So what is the Z transform? A summation from k0 to infinity, yk is set to the minus k by definition. If you want to do it that way, straight away you start with Laplace, Z transform definition. And earlier you start with the Laplace transform, right? I really wanted to show you that this is not completely different two things, but it's very well connected. But you can start your process either way, right? Straight away through Z transform definition, or you can start the process through Laplace route, and at some point substitute Z for S, take that out. All right. Or if you know the sequence like this, you can straight away write down with the delay operator, Z to the minus 1, Z to the minus 2, Z to the minus 3, and you get the infinite sequence and get the summation of that sequence, right? Like this. So you can see yk Z to the minus k, right? Is here, and e to the minus kt, you can write it like that, e to the minus t, Z to the minus 1. K can be taken out as a common factor, and now you call this as alpha. What is alpha? E to the minus t, Z to the minus 1. Okay, because k is common to both of them. So the sequence is now very simple, right? Same thing we are repeating with some non-numerical values for k for t. So it's 1 plus alpha square and so on, and you get the summation, work it out. I don't need to go through this again. It's pretty clear. Okay, so get Z over Z to the Z minus e to the minus t, right? So this is the Z transform of an exponential function, right? And I have here the Z transform table for known functions delta n, un, bn, and so on, right? Just keep it as a reference, right? Whenever you want to solve Z transform sums, this table is very, very helpful. Right. So the next topic is inverse transform, and certainly we will take it next Sunday. Right. Any questions, please? Please do the homeworks, right? You don't have to submit anything. I will upload the lecture note so that you can refer to it. Any questions? All right. In that case, we'll stop for the day, and I'll see you next week.
Thank you, sir. Good evening.
Thank you, and have a good night.